Okay, hello again. So I'm gonna focus on switching losses right now. So switching losses relates to losses that happens in diodes and transistors as they want to turn on or off. So like so far we've assumed that these happen just like instantaneously, like as soon as the voltage goes to zero, the current starts flowing through the circuit, but that actually doesn't happen instantaneously, right? There's some delay and so we have to take that into consideration. But before we start talking about switching losses, I want to mention that like why calculating power losses is important. Mainly because if you don't calculate it, if you don't consider losses, right? And let's say like you don't design a heat sink or a proper heat sink for your power electronic devices, then like everything is gonna melt. Everything is gonna basically burn, like, or like some like they might get damaged, or like they might not perform ideally because performance of electronic devices can change with the heat, right? So like you have to make that take that into consideration. Also, like you might not be using your battery very efficiently if you have like so much losses, and if you don't take that into consideration, so your battery life might get affected. One thing that we should mention that is like all the calculation we do, like we have some parameters, right? So like our input voltage, output voltage, switching frequency, load current, these are the parameters that we know. Let's say like if you want to compare two different devices, let's say like some salesman wants to sell something to you, and they say like, oh, this device has 90% efficiency, the other one has 95%. Okay, so the question that you should ask that salesman is like, okay, what are the parameters, right? Like for what input voltage, for what output voltage, for what switching frequency, for what load current, it has 90% efficiency or 95% efficiency, right? Because one device can have like, let's say 95% efficiency for a certain voltage and like another efficiency for another voltage, right? So these are the parameters that you have to know. Now let's get back to switching losses. Okay, this applies to both diodes and transistors. Okay, so first let's see where does that come from. I have the plot of sorry, like this is collector emitter. Sorry, this is like the transistor that we have. Like it can be a MOSFET or transistor or a BJT. So like here you see that at this point you're turning off the transistor, right? So you see that voltage of CE is 0, means like the transistor is on. Now it's getting off, right? So there's some current flowing through this collector. Now it just like basically goes to 0, right? So this part is the switching. This is like when you're turning the like basically stopping the signal, the voltage signal to the base. So that's basically what's happening here. Now you see that this is our voltage, this is our current, right? These changes doesn't happen instantaneously at the same time. So there's some period that it takes for the voltage to reach its final value and for the current to be close to 0. This is gonna have some losses which you can calculate by integral of vi dt, right? The same thing happens here. Okay, so when you want to turn the signal, when you apply a voltage here or here, apply a voltage here or a current here, basically your voltage is supposed to get to 0. It might not be exactly 0, but like it gets to close to 0, and then the current starts flowing from collector to emitter. So this part also takes some time. So we have some losses for turn on and turn off. so that's where the switching losses come from. One thing that I should mention is that we are simplifying things like in our models, right? This is like this is like a more realistic waveform of current and voltages. Like during the switching, you see like there's so many oscillations here, and like there's like a big jump here, another oscillation here. This might go like a little bit higher, and like this might not be exactly zero. So in our modeling that we are doing here, we do some simplifying assumption to take power losses due to switching into consideration. It might not be very exact. So if you simulate your circuit using MATLAB or using PSCAD, you might have a different value, but this calculation that we are doing, it's simplified. So let's just start doing that. So let's say we're doing this for a MOSFET, and this is V of gate. So we're applying a voltage towards the voltage at the gate at this point. Okay. And I'm just drawing VDS, ID, and power. This is switching power losses. Okay, so let's start with that. So let's say at this point, like we are turning the voltage of the gate on. So we are basically like, you're gonna have like some before that, like the current is 0, the current from drain to source. So then at this point, like let's say at this point a little bit further than that, like with some delay, it's gonna start going to what it needs to be, right? And then before this point, the voltage was high, right? The drain source was open, so you had an open source voltage. When the current reaches that final value, then the voltage, it's gonna slow down and move towards 0. It might not be exactly 0, but basically this is like how much it takes to get to its final value, right? So it takes some time for the current to rise, T sub R, rise, current, and it takes some time for the voltage to fall down, T sub fall voltage, right? So if you basically multiply these V and I by each other, VDS, IDS, if you calculate the instantaneous power, we would see that we have some power